Okay, welcome to the next class on multiple view geometry. Last time we talked about the 8-point algorithm, and the challenge, I show you this picture again to start off with, is that we assume we are given two views of a 3D scene, and we observe the same points in the two views. And say the point is P, then we observe its 2D coordinate in the first image, x1, and the 2D coordinate in the second image, x2. And we have such pairs of corresponding points in two images for a number of 3D points. For a number of points like P, we observe their 2D coordinates. And so there are two challenges that we try to resolve. One challenge is to estimate how did the camera move from one image to the next. That is the rotation and the translation that gets us from the first coordinate frame to the second coordinate frame. And the second thing we want to estimate is the 3D structure. And so this problem, so that means the location of the points in 3D. And really all that we need once we want to reconstruct, say, in the coordinates of the first frame, is the distance of that point from the camera center. And once we have that, we can just extrapolate through the corresponding point according to that distance, and then we get the point. This is the structure problem, and so in computer vision this problem has traditionally been called structure and motion. Motion being the camera motion, structure being the 3D point coordinates. What we talked about last time, let me go straight to the respective slide that summarizes it all, is the so-called 8-point algorithm. This was a breakthrough in that context, an algorithm published in '81 by Longet-Higgins that allows to compute the motion of the camera without actually having access to the 3D coordinates. We saw the whole problem is a chicken and egg problem. The approach by Longet-Higgins, this 8-point algorithm, allows to decouple that chicken and egg problem. And it says if we have enough points that we observe in two views, and enough in practice means at least 8 points observed in two views, then we can actually determine the camera motion without, in closed form, without actually looking at 3D. And the way it worked, maybe to reiterate, was based on the so-called epipolar constraint. Let's go back a few slides. This is the epipolar constraint. The way it came about, to remind you, is that we did the projection of the point into the first image, and lambda 1 is the depth with respect to the first image. So maybe I'll make a drawing. We have a structure here. We see a point in one image and in another image. And this distance from the camera center, O1, this distance we call lambda 1. And this distance here from the other camera center we call lambda 2. And this is x1 and this is x2. So this is the drawing that's going to accompany us for a number of lectures now. And so the transformation from one camera to the other, this here is rotation and translation that is unknown. The depth parameters are also unknown. But we have two equations modeling these, and if we appropriately insert one equation into the other and then do certain transformations, we end up with an equation down here that is called the epipolar constraint, and that couples the coordinates of our point in the first image and those in the second image with the camera transformation parameters. And mind you, this is important, there is no 3D information in that equation. There is the large x, that is the 3D coordinate of that point, is no longer there. And also the lambda parameters representing the depths, they are no longer in this equation. So it's an equation that directly couples the 2D coordinates and the camera motion. It's not an equation that allows you to directly extract the camera motion. And in order to do that, we take a number of such constraints and stack them, combine them appropriately in a matrix system. And this is what we did here. So we rewrote with the essential matrix. T hat R is the essential matrix. This is the epipolar constraint. We wrote it as a scalar product of two vectors, one containing the known 2D coordinates and one containing the unknown camera parameters. And so we see that the projection of that stacked vector of the essential matrix on A must be 0. And now we do that not for just one point, but for a number of points, say little n points, where n in practice is going to be 8 or more. And this is the matrix, and then we can say E is the vector that defines the null space of that matrix chi. And what we want is, we said that the whole reconstruction only makes sense up to the scale factor. And so the extreme case is scale everything to 0. That's a valid solution. And that amounts to having E being 0. That clearly fulfills this equation. But we don't just want 0 as a solution. We want a one-dimensional null space to have a unique solution, unique up to scaling. And that we can do by imposing the null space should be one-dimensional. That means this 9 by n matrix chi should have rank 8. It has at least, at most, rank 9, because it has, as you can see, this is a matrix. Each A is a 9-dimensional vector, so it's a 9 by n matrix, so the rank is at most 9. If we want a one-dimensional null space, we have to assure that it has rank 8. If it has less than rank 8, so if we take fewer than 8 points, then the null space will be not one-dimensional, but 2 or more higher dimensional. Then we don't have a unique solution. This is why we need 8 points in order to assure a unique solution to the problem. And that leads to this 8-point algorithm where the solution is then, you remember, computed by singular value decomposition. We compute that matrix, we do a singular value decomposition, because with real world, measurements, this is never going to be exactly 0, so we minimize this expression. We minimize the norm, and if you do that, then you get to the singular value decomposition. You find that E must be the 9th column of the V matrix in this SVD. That corresponds to the smallest singular value. And then we do the projection on this essential space, because we know once we unstack ES, it must be an essential matrix, and we know essential matrices have the 3rd singular value being 0 and the first 2 being identical. And since the scale is not defined anyway, we can fix that non-zero singular value to 1. So this is called the projection onto the normalized essential space. And once we have computed the essential matrix in this way, we can extract rotation and translation. There are multiple possible solutions, in total 4. So 2 possible rotations, 2 possible translations, where this is a rotation around plus pi over 2 or minus pi over 2. So it's either plus 1 minus 1 here, or minus 1 plus 1. You can recognize rotations around the z-axis in particular because they preserve the z-coordinate. So if you apply this transformation, this rotation matrix to a vector, you see that the z-coordinate is not affected. And that is characteristic for rotations around the z-axis. So this way we can compute rotation and translation from a set of point pairs in 2 images. We need 8 or more point pairs. We talked about how many we really need. We also talked about degenerate configurations. We'll see a little more of such degeneracies today. What we start with today is, now that we have rotation and translation of the camera, now we want to recover the 3D geometry. And I'll show you that this problem as well can be solved using linear algebra methods. And so the key and say the core component of this class is to show you to what extent we can apply linear algebra techniques to solve these multiple view reconstruction problems. So we saw rotation and translation in the 8-point algorithm can be determined by singular value decomposition, and similarly the reconstruction can be computed. So that is, we now assume we have translation and rotation, but remember the translation is really only defined up to scaling. And you saw that in the 8-point algorithm we fix certain parameters to 1, but if we want to keep that ambiguity, that degree of freedom, we can do that by saying, let's consider the scale parameter gamma. So gamma is some non-negative number that defines the length of the baseline here. So this length connecting the two camera centers, this we call gamma. So we have a translation, but we can only determine it up to that scale. And so we keep that parameter scale in here, and then what we have for all images, we see that for any point, and now we consider multiple points, this is why we have so many indices, please don't get confused by all the indices, j is just the number of the point. And so here for all n points, j going from 1 to n, we have these equations for the second image. So this is x2 for the point j, here we have xj. And then if we relate these parameters, we see that lambda 1 xj1 is nothing but large x. So this is lambda 1 for the j's point times x1 for the j's point, little x1. This is x1j. And then if we rotate and translate that into the new cameras, this is this expression, then we get lambda 2 x2. And so this is the equation that relates the 2D coordinates, the depth parameters, rotation and translation. What's important now is to always keep track of what are the known parameters and what are the unknown ones. Here, the known parameters are the 2D coordinates, little x1, little x2. We always assume we have these. The known parameters now are also translation, rotation. We have computed them with the 8-point algorithm. The unknown parameters are the depth values, lambda 1 and lambda 2, and the scale parameter gamma. That is unknown, but in some sense will remain unknown. Now we want to simplify this expression, this equation, and we can do that very much like in the derivation of the epipolar constraint. We can now apply transformations to this equation, and the transformation we'll apply is aimed at kicking out the parameter lambda 2. We want to remove, we have too many parameters in the equation, we can remove one by multiplying with x2j hat. x2j hat is a matrix that models the cross product with x2j, and one of its effects, if we apply it from the left hand side here, is that this term becomes 0, and in that way lambda 2 drops out of the equation. And so the left hand side here becomes 0, and the right hand side becomes, we can pull out lambda 1j, it's a scalar parameter, so we have x2j hat r x1j. And here we have similarly have gamma times x2j hat times t. And so now we have a constraint that couples, that is a linear equation in lambda 1j, the depth of point j with respect to the first camera, this one here. So for point j, this is lambda 1j. And the scale parameter gamma. All the other parameters are known, and so this is nothing but a linear system. And we have n such linear systems, one for each point that we observe. And so we can write that, if you like, as a linear system. You can extract the unknown parameters, put them here, the known terms on this side, and so this term times this vector here, this matrix times this vector is 0. This would be the matrix vector representation. And so now you see this vector, two-dimensional vector, lives in the null space of that matrix. It's a vector that is mapped to 0. We can do that for all endpoints, and in fact we can combine all these equations into one big equation, and this is what it looks like. So now we do that for all endpoints. So we have lambda 1, 1 to lambda 1n. That is the depths of all points with respect to the first image. And then we see that we have a linear equation system combining all these linear equations into one big equation of the form m times that vector lambda is 0. And the matrix M looks like that. In fact, if we go back, here you see x2j are x1j times lambda 1j plus this one times gamma, and that's exactly what we have here. If you look at that, for example, the first row gives us an equation for the first point saying this expression times lambda 1, 1 plus this expression times gamma equals 0. And so all our equations are here in these separate rows. Yeah, it is possible to directly extract these. Here we want to solve the issue is you can try to compute the depths of each point separately. But in some sense, we want a reconstruction that is consistent in some sense. We want to recover all the depth values. And in practice, you know, with numerical errors, there may not be a point. You know, in practice, it may well be that if you try to triangulate the rays, they don't actually intersect. And then the question is, what do you do? And here what we do is we try to solve the whole thing in one go. Find one solution for all depth values and a scale parameter that is consistent. So this is, before we start solving the problem, we first formulate it as an overall problem. So rather than iteratively estimating the depths of each point, we try to do it jointly. And it's important because we have an unknown scale parameter here, and depending on how we choose it, everything changes. All the lengths change, right? If we scale the baseline by a factor of 2, we have to scale all the depth values also by a factor of 2, for example. And so we want to solve this equation system. In practice, it's not going to be exactly 0. This is the thing, that we only have approximate solutions, we have errors in it, and so what we do is we do a least squares solution. What that means, I didn't write it on the slide, but it actually just means that we minimize, we find the vector lambda such that m times lambda is minimized. The square norm is minimized. And if you do that, then you minimize over lambda, lambda transpose m lambda. And of course, this is minimized, among other things, by setting lambda to 0, right? If we put the scale to 0 and all the depth values, everything shrinks to a point that, as I mentioned, this is always a valid reconstruction. So what we need to additionally impose is we need to impose that lambda is unit lengths, let's say. And if you do that, minimize this expression under the constraint that lambda has length 1, what you get are the eigenvectors, the eigenvector to the largest eigenvalue. So if I minimize this under such that lambda norm equals 1, then what I get is the eigenvector to smallest eigenvalue. Eigenvalue of M, M transpose M. And so this is how formalizing it as the whole thing as a least squares problem, saying I may not get this exactly to 0, but find me a lambda such that this expression is as small as possible, then I get the eigenvalue solution. And so we see very nicely that we get a closed form solution to estimate simultaneously all depth values and the scale parameter. Of course, up to the scale freedom. And the scale freedom is in here that we say, well, just some unit length vector. And then all scaled versions of lambda are similarly feasible solutions. And then ultimately this question of what scale do you choose for the reconstruction is really up to you. Usually you would say, well, how big is my screen? And then choose the reconstruction width, the size in a way that it fits your computer screen if you want to visualize it. But as I said, from just images, we'll never get the scale of things. We have to have some additional measurement if we want to have absolute scale reconstructions. So what you see is, again, just like in the 8-point algorithm to estimate the camera motion, here as well, in the estimation of the depth parameters lambda, the structure reconstruction, the structure estimation, we could use linear algebra techniques and eigenvalue or singular value approaches. And these approaches, the nice property of them is that they're closed form solutions. You can say the solution is the eigenvector to this smallest eigenvalue. And this is often called an analytic solution. To be very honest, if you go deeper into things, at some point you wonder what is exactly the definition of an analytic solution over a numerical solution. Usually you say you call this an analytic solution because you can say it is the vector to the smallest eigenvalue. In practice, of course, once you have to compute it, you have to, switch on the computer and numerically compute the eigenvalues and the eigenvectors. That's also a numerical algorithm. So, of course, at that point, the distinction between a closed form solution, an analytical solution, and a numerical solution is a bit vague in some sense, right? I just wanted to mention that because there are other algorithms which are not considered closed form because they minimize some cost function and do that iteratively. But, ultimately here you also have to iterate some numerical algorithm to compute eigenvalues. So the distinction is not so large in many cases. Here's an example that was provided by Jana Koseka, one of the authors of the book that we work with in the class. There's two images, these two here, and you see there is correspondences marked, so there's a lot of points here and points there that are marked. I don't know, to be honest, for this example, whether these correspondences were actually determined automatically or manually. For the sake of this part of the reconstruction, it doesn't really matter. We assume they're given. But the question that will haunt us a little more is, of course, what happens if these correspondences are not perfect? If they were set manually, but the user made some mistakes in actually localizing the points, or if they were computed automatically and the machine got an inaccurate correspondence, that will happen in practice. Here's the reconstruction. So these reconstructions, I must admit, at least last week one of my students presented some state-of-the-art reconstructions, and compared to those reconstructions, these look a little bit toyish, because really you see the two camera poses were estimated, and the reconstruction actually amounts to only finding the location of these points that you found correspondences for. And you can see already the major challenge is, if I just have a selected number of a few hundred points, how am I ever going to see the 3D structure that is there? What do I do? Do I interpolate these points? Do I fit a mesh to it? Is that going to be a good reconstruction? This is a separate challenging problem. So, excuse me? Yes, you can triangulate everything, but then how do you connect this point to other points? Where do you place triangles? You don't want to put triangles for any 3 points, right? I'm not going to take these 3 points and fit a triangle to it. So it's a little bit difficult how to do that. I mean, there are standard techniques to do triangulation, but they are invariably going to be suboptimal. Once you don't have enough points, you will see artifacts. Yes.
You can only estimate like 7 points.
Yes.
And we cannot reconstruct just a simple geometrical object.
Yes. That would be one approach to not just reconstruct points but lines in space, and actually have the 3D reconstruction of a line. That would improve things, definitely. The way things are done today is usually that you apply a kind of a pipeline of algorithms, where you would start with linear algebra techniques, maybe to get an initial estimate. You would use these techniques maybe to get the camera transformation. But then subsequently, once you estimate geometry, you often revert to other algorithms where you directly estimate a dense surface, for example, and not just a set of sparse points. But anyway, so this shows you a little bit what you can do with it. You can indeed address this chicken and egg problem of determining how did the camera move and where are my 3D locations. As I said, in practice, there are issues. In practice, the question is, do I actually have the correct correspondence? It is a closed form solution, as I said, but you know, what really means closed form, if you have to numerically estimate eigenvalues and eigenvectors, there is ultimately also a numerical process involved. You estimate the camera parameters, the 3D structure, you use singular value or eigenvalue decompositions. But the issue is, in reality, the correspondences are not perfect. And then I said the question is really, what are you optimizing? Once you apply this strategy, what happens is a number of things. If you observe, here I will call them x tilde is the observed 2D coordinates, so not the true one that should be with the 3D location and the camera transformations, but the one that the user or the computer labeled and said, here's the corresponding point, and that may not be the correct x2, but slightly off. And there are two deviations, to be honest, and typically people distinguish one. The first case is that it's slightly off, so there's a little deviation, it's not exact. The second issue is it may be the entirely wrong point that I labeled. Say if you have a checkerboard and in one image you have a corner and then you mark a corner in the other image, or the computer does, maybe it's the wrong corner. So it's not just slightly off, but maybe completely off. This is then often called an outlier. And depending on what kind of errors you have, you're going to revert to different approaches to tackle this issue. But the issues that you will find is that once the correspondences are inaccurate, you have no guarantee. Even if they're only slightly inaccurate, you have no stability properties. Stability here means that if the correspondences are only slightly off, I would ideally want a solution where also the rotation and translation are only slightly off. So if the estimated correspondences are close to the correct ones, then I would want a solution where the estimated camera transformation is also close to the correct one. So some kind of robustness, if you want. Slight errors in the measurements should only lead to slight errors in the solution. Unfortunately, for this solution, this is not the case. And the reason is inherently related to the mathematical problem of eigenvalue estimations and eigenvector estimations. And there are many cases where slight changes in a matrix have an effect of drastically changing the eigenvector structure. So we have no guarantee that the estimated rotation and translation are as close as possible to the correct solution. In addition, the second problem is that we have no guarantee that we will get a consistent reconstruction. So once we run our 8-point algorithm, it gives a rotation translation. It may well be that there is no 3D point that is consistent with the 2D coordinates. And then the question is, what do you really do? You have no intersection, and it turns out just taking a point that is in some way close to the two rays is a suboptimal solution. There are often intuitive strategies that people revert to and say, oh, if the lines don't intersect, I find a point in between that is as close as possible to both lines. That is one solution, but one can show that this is not necessarily the best one. So these are some of the difficulties you face. And here's, to go back to something I mentioned in the beginning of the reconstruction problem, here's what you can do to resolve this issue. One approach to work with noisy data in practice, and this goes well beyond image processing, but any field of science, once you have real-world noisy data, a solution to the problem, a good, robust solution, is usually obtained by reverting to statistical inference techniques. And the way these go, in case, has anyone heard of these before? Statistical inference, Bayesian inference, maximum a posteriori estimation, yeah. So these are the kinds of techniques. The way they work, for those who haven't heard of them, is that you say, I have some measurements, x tilde are my measured 2D coordinates. And now what I want to estimate is rotation and translation of the camera and the true 2D coordinates, little x. So I have true 2D coordinates that are consistent with the 3D points, and I have estimated 2D coordinates, and they are not necessarily the same. So I explicitly allow a deviation. I say this is the correct correspondence, but then my human labeler or my computer told me, oh, it's here, the point is here. And this is xj tilde, so this is the estimated point, but it's not the same as the correct point. And there's a little offset, a little deviation that I explicitly allow in this model. And then I say, fine, and this is a conditional probability distribution where you say, find the most likely 2D coordinates and rotation and translation of the camera given the estimated 2D coordinates, x tilde. So that is now, little x would combine all 2D coordinates of all the points that I observe. And then there is the so-called Bayesian formula that you can use to rephrase that, and you can say this is equivalent to saying maximize the probability of observing these 2D coordinates given the true ones and the camera transformation times some prior probability on how likely are different rotations, translations, and 2D coordinates a priori. And this is called the prior or a priori distribution. This would be at least a formal way to tackle the problem. Whether it's really a practical way is a matter of opinion, really. The issue is that if you want to model probability distributions here, it's not a nice thing to do, because the space of camera motions is here SO3 times S2. Typically you would say SE3, we saw the rigid body motions, SE3 is rotation translation. Here if we say we don't know the scale of the translation, then it's S2. S2 is the sphere in R3. Unit sphere, and that is the 3D translation with unit lengths. So I say I want to estimate the translation, but I impose it should be unit lengths. I fix the baseline to 1, and then I have a space that is this one. Rotations times times unit lengths vectors in R3 to model the translation direction. And that's a fairly complicated space. And then you have to define a probability that lives on that space, and it's not a nice thing to do, and a bit tedious. One alternative is to formalize a constrained optimization problem. Now I'm saying it's an alternative here, but really there's a lot of relations. In fact, you get exactly these expressions if you assume a uniform prior. That is often done in statistical inference. If you don't, here you can impose what is more likely as rotation and translation. And if you say, I don't know anything about what the rotation and translation was, that means all rotations and translations are equally likely, and that means that this term is just a constant. And then I can drop it. And then if here I work with a Gaussian distribution, then I get exactly that. So this is, in some sense, a specific instance of that model, a little simpler model. And so what we have here is a cost function where I say find 2D coordinates in the images, the true ones, and rotation and translation, such that the error between the estimated correspondences and the true ones is minimized. So what I'm doing is I'm just minimizing this discrepancy. Find a reconstruction that minimizes what would be called maybe the projection error. I have a reconstruction, it projects to these points, and now I'm saying do a reconstruction such that it's as consistent as possible with the observations, and that I really minimize this geometric error. Now this is something everyone would agree that's useful, that's a good approach to solve it. The eigenvalue solutions we saw earlier, the 8-point algorithm, all of these, they don't do that, they don't minimize the projection error. So they have closed form solutions, they nicely decouple the problem of structure and motion estimation. That's the good side. The bad side is they do not minimize this projection error. Because once you tackle the problem as minimizing this projection error, it's much harder to decouple the structure and motion problems. And so you do that under the constraints that you want a consistent reconstruction. Consistent reconstruction means the true 2D coordinates should fulfill the epipolar constraints. So the difference of what we do now compared to before is we say not the measured 2D coordinates fulfill the epipolar constraint, but the true ones. And the true ones are close to the measured ones, but not necessarily identical. So that's kind of a relaxed reconstruction where we say, hey, maybe the correspondences that the algorithm gives us are not the right ones. So find a reconstruction, meaning some 2D coordinates and a camera transformation that fulfill the epipolar constraints. These last two constraints, they're just saying that the third component must be 1. E3 is this 0, 0, 1 vector, so it just means that x1j is the 2D coordinates in is the 2D point in homogeneous coordinates, meaning the third component here is 1. So, because the epipolar constraint, all of that was in homogeneous coordinates. So in other words, we want to find points on the image plane, and this says they live on the image plane of the first, in the first image and in the second image, and they fulfill the epipolar constraint, and they are as close as possible to the estimated 2D coordinates. And this is a constraint optimization problem, and we've talked about it before. Essentially, these approaches are known as bundle adjustment. There are many ways to parameterize these cost functions. For example, and I want to show you a little bit because this is often an issue in research and in science. You have hundreds of papers on the topic of reconstruction. And at the first glance, they all look different. You read one paper and then you read another and you don't see the relation. And somehow, this is not uncommon in science. After reading a number of papers on the same problem, the same topic, you get the impression that really people are doing the same thing. Except you don't see it directly. But often, it's not surprising really that people, if they tackle the same problem, then it's not surprising that they may end up with doing the same thing. But it's not often visible at the first glance, the reason being that you can parameterize these problems differently. So what I showed you just now is we want to minimize this discrepancy. The question is, how do we parameterize it? In this formulation, we parameterize it in rigid body motion and the true 2D coordinates in the two images. What we can do instead is we can parameterize it in 3D coordinates. We can say we have 3D coordinates xj, so that is this point, and we have rotation and translation, and we want such 3D coordinates and rotation and translation that the projection is close to the observed point. So this is the observed point in image 1, the observed point in image 2, and this is the projection onto the first image, and this is projection onto the second image. So that would be a parameterization in the 3D coordinates. What we can instead do is we can parameterize the whole thing in the 2D coordinates of the first image. If we do that, then the first term is extremely simple. Here we just have the 2D coordinates in the first image. And these should be close to the measured 2D coordinates. Once we go to the second image, what we have to do is we have to transform that point x1j to R3, that is then lambda 1j x1j, this here. Then we rotate into and translate into the coordinates of the second camera, rotation of that 3D point plus translation, and then pi is the generic projection onto the second image plane. So that is the projection that maps it just down to that point. And the point where I end up with should be close to the observed 2D coordinate, close in that least squares sense. And this is often called bundle adjustment, but as you can see, we have the exact same cost function. We just rewrite it. So the cost function is a cost function that measures the discrepancy here. This error from the measured 2D coordinates and the real 2D coordinates in both images, summed over all points from 1 to n. And so you see that this cost function is really the same as this cost function. Here we have I1 to 2, so that would be for the first image and for the second image, so this is just a sum of two terms. This is the two terms, so the question is, where do you choose your parameters? Do you want to optimize in the image plane? Do you want to optimize in 3D space? It's really up to you. Yes?
But in this way we are, let's say we are relating, we are putting the quality of measurement related to the first camera. Let's say if I can have two different camera images taken two different cameras, or let's say even if they are the same camera, there would be some differences in the sensor. So we are just taking account the quality of the first camera?
Not really. See, we are also, this is the quality in the first camera, the discrepancy to the first measurement. Here we have the discrepancy to the second measurement. So at least on that level there is a certain symmetry. But you're quite right, the parameterization of the problem is in the first camera. It's not in the second, and so there is, it's not entirely symmetric. Here is perfectly symmetric, here not so. I mean, perfectly symmetric is maybe not quite right. It depends on how you do the projections. Typically, you work in 3D coordinates with respect to the first camera, and then pi1 is just the generic projection, whereas pi2 is the generic projection after rotation and translation. And so the rotation and translation are in the second term. I mean, if you wanted to express everything in the second camera, then you would have the inverse rotation translation, the inverse rigid body motion here. I mean, there's a degree of freedom of how you parameterize things. And, you know, not surprisingly, depending on how you choose the parameterization, the problem looks different. At the first glance, you wouldn't say that this is the same as that. It looks very different, but if you take a closer look, you see at least what the cost function penalizes is the same, is that projection error. And so this is an unconstrained optimization problem. Here it's unconstrained as well. Here, see, we estimate x1 and lambda, and actually the product of x1 with lambda is nothing but the 3D coordinate. This is an unconstrained optimization problem. Here you have a constrained optimization problem. In practice, I must admit, unconstrained problems are nicer to solve. Constrained optimization is a little bit more involved. I don't know how much you learned about optimization. There are many ways to impose constraints in the optimization. There's the most common one is the approach with Lagrange multipliers. So for each constraint, you have a Lagrange multiplier to impose that. And often it's nicer to do unconstrained optimization if you can. I mean, unconstrained, this is unconstrained in some sense, but then if I say R is a rotation matrix, it's not so unconstrained either. Remember, the rotation matrices SO3 is a fairly complicated group structure with determinant 1, with orthogonal matrices. R transpose R must be the unit matrix. These are constraints as well. So although this looks unconstrained, if I say R is a rotation matrix, you know, and it has to be a rotation matrix, all of a sudden I have constraints as well. And then, but one way to solve this, to go a little deeper, would be to represent R with the Lie algebra, as we've seen earlier in the class, with the skew-symmetric matrices, and then you have your skew-symmetric matrix parameters, and these three parameters are really unconstrained. And then you use the Rodriguez formula to write R as a function of these parameters in here. And then you have a fully unconstrained optimization problem. So we saw the 8-point algorithm allows to estimate camera parameters with linear algebra techniques. We can also estimate the structure with linear algebra techniques. One of the things we saw is that in the 8-point algorithm, typically 8 points or more are 8 points are enough, except if these points are on a degenerate configuration. And I mentioned there's a number of degenerate configuration. These configurations are typically 2D surfaces in R3, and these surfaces are called critical surfaces. Typically, these critical surfaces can be described by quadratic equations in the 3-point coordinates, and this is why they're called, referred to as quadratic surfaces. Most of these surfaces are pathological cases that don't actually happen in the real world. But one particular case of a quadratic surface that does appear frequently in the man-made world is the plane. And I guess, you know, we wouldn't be talking about this if men hadn't started building houses and putting planes and, you know, paving roads, and all of a sudden the world we live in has a lot of planar structures. You know, if this is an interesting aspect, that really these degeneracies, the only reason they come in is because we as humans built our world in this fashion. In the real world, you don't typically see flat surfaces. Unless maybe if you see the surface of a lake, a water, it can be quite flat as well. But usually in nature you don't have such planes. But in man-made worlds we do, and a lot of the reconstruction stuff that we do is often actually focused on these scenarios. We want to, say, Google Earth, we want to reconstruct cities, we want to reconstruct planar structures. And if I hold a camera and walk around, if I'm too close to the wall, chances are I only see the wall, and chances are all points that I track are on that planar wall. And then we have a degenerate case where the 8-point algorithm doesn't work. Then I can take as many points as I want, 8, 9, 10, even more. If they all lie on the plane, I'm not going to get a unique reconstruction, not with the 8-point algorithm. Fortunately, for the case of planes, there exists an algorithm that is actually even simpler than the 8-point algorithm, and that can do reconstructions of structures where all points lie on the plane. This algorithm is called the 4-point algorithm, and so the assumption of the 4-point algorithm is exactly the opposite in some sense of that underlying the 8-point algorithm. So in the 8-point we say we want 8 points and they should not lie on a plane. Here we say we want at least 4 points and they should lie on a plane. So the assumption is that I'm tracking and all corresponding points are part of a plane. So in some sense I assume I insert the knowledge that the structure I'm looking at is a planar structure. That's a very strong assumption. But it happens frequently, and in fact there are a lot of algorithms in computer vision that work amazingly well under the assumption of planar structures. Has anyone seen Google Goggles? It's an app for smartphones by Google. Yeah, so that is an application that works very well for recognizing structures as long as they are planar. If you try and work with it, as soon as you take images of non-planar structures, chances are it's not going to work. And in fact, this is one of their open challenges right now, is to extend these techniques to non-planar structures. For planar structures, the stuff works quite well, though. And this is not uncommon. A lot of recognition techniques, a lot of computer vision techniques work with the assumption that the object is planar. And the hope is that if it's close to planar, it still works fairly well. If that's the case or not, it is a matter of opinion. But so this planar assumption is a common one, and fortunately in a lot of the things we do in the world, if you want to detect, for example, Google Goggles works extremely well. If you have a book and you have the cover of a book, you can take a picture and it tells you immediately what book you're looking at. It tells you what the price is, everything, right? Why? Because the book is planar. So for that, it works, and a lot of the stuff, the things we have in the world have planar structures. What can we do if we have a plane? Let's look at planes. Let's start by saying, how do we actually represent planes? So here's a plane, and there's our origin. So that's a plane in the 3D world. Here's the origin of our camera, and the plane is characterized by a normal vector, n, or maybe I put it this way, here's n. And then there is an offset, so this is the offset, we call it d. is the offset from the origin. And once I define the normal and the offset from the origin, that distance from the origin, that defines the plane. And then I can say for every point on the plane, here I call it large x1 is a point on the plane. It's defined by the fact that if I project that point, that vector here onto the normal vector, then I get exactly d. So the component of x in the normal direction, this component here, has length d. So this is the equation, and that is true for any point on the plane. So this is the equation that governs points on the plane. If the plane is defined by a normal vector n and an offset d, then any point on the plane fulfills this equation. And vice versa, of course, any coordinate vector x that fulfills this equation is on the plane. So this is the equation that describes that plane. And if I rewrite that, I just divide by d, then I can say 1 over d n transpose x1 is 1. So for any point on the plane, this expression holds. This equality holds. And now what I can do is I can look at, now we look at the same point on the same plane from a different camera, and that is x2 is the 3D location in the second camera. x1 is the 3D location with respect to the first camera. x2 is the 3D point in the coordinates of the second camera, and as you recall, it differs by rotation and translation. rx1 plus t is the 3D coordinate in the second camera. And now what I do is, this is a trick, here I insert the 1. See, I have 1. I insert that 1 in here. Because I know 1 over d n transpose x1 is 1. And so then I can extract the vector x1, and I have a matrix R plus 1 over d t n transpose times x1 is x2. So I can write the point in the second coordinates as a matrix times the same point in the first coordinate. And this matrix, we call it H. It's called a homography matrix. So for any plane that I can consider defined by normal vector and displacement, I can construct such a homography matrix. And you can see this matrix is made up of a rotation plus then parameters involving translation, displacement, and the normal vector of the plane. That's a 3 by 3 matrix, and so I can say that once I look at points that live on a plane from 2 cameras, no matter where the cameras are, as long as these points live on the plane, the transformation from one camera to the other can be done by a 3 by 3 matrix transformation. And that is interesting because in general that's not the case. In general the transformation involves a rotation and a separate translation. And I can write it as a matrix product only in these homogeneous 4D coordinates in the general case. But in the planar case I can write it as a 3 by 3 matrix acting on the 3D coordinates. And you can, and the same holds actually for the 2D coordinates in the 2 images, little x1, little x2, because little x1 times lambda 1 is large x1, little x2 times lambda 2 is large x2. And so we have this expression connecting the 2D coordinates in homogeneous coordinates, mind you, so the third component here is 1, here as well. It connects them with the same homography matrix. And this expression, so you can, you have these scale parameters, but as you know, remember you can also write this in this way, where tilde means the 2 vectors are the same up to scaling. And this expression is called a planar homography. It models the transformation from that 2D coordinate to this 2D coordinate. And so that simplifies our life drastically if we can say the 2D coordinates differ by some matrix multiplication up to scaling. What's important is this homography matrix depends on the camera transformation and on the plane parameters. But it does not depend on the 3D coordinates. It does not depend on the 2D coordinates. And what we can do now with this additional knowledge, working with the assumption that what we observe is on the plane, we can now reformulate the epipolar constraint and get a so-called homography constraint. Sometimes it's called planar epipolar constraint. The way it works is as follows. We know x2 times lambda 2 is h lambda 1 x1. We have that connection between the 2D coordinates. There is some homography matrix connecting them. We don't know what the plane parameters are. We don't know what rotation and translation are, but we know there is some matrix H that contains them and that couples the 2D coordinates. So a little bit like this essential matrix we'll see in a second. In fact, what we can do is now we apply x2 hat from the left side. Why? We want to kick out these scale parameters lambda 1 and lambda 2. Remember, we did that in the derivation of the epipolar constraint as well. We want to kick out anything that reminds us of the 3D world here. And these are the scale parameters. We do that, we apply x2 hat from the left. This term becomes 0, and on the right hand side we get x2 hat h x1 times lambda 1, but we can just divide by lambda 1. And so we get this expression that couples the 2D coordinates and the homography matrix H. And so it's quite reminiscent of the epipolar constraint, where we also had a matrix coupling the 2D observations, the 2D coordinates. And so in analogy, this is called the planar epipolar constraint. And what we have in the matrix here, much like in the essential matrix, it contains rotation, translation, and the plane parameters. Normal vector of the plane and this offset D. It's all somehow mingled in that matrix H. And so much like with the epipolar constraint, much like in the construction of the 8-point algorithm, I can do the same now for this planar assumption. I can start with one constraint for one point observed in the two images, and then do that for multiple points. So I get multiple planar homography constraints, or planar epipolar constraints, sorry. And what did we do? We stack the vectors, so we separate the known 2D coordinates from the unknown camera transformation, or this homography matrix. We stack the 3x3 homography matrix in a 9-dimensional vector. Here it is, h11 to h33. And then we do the Kronecker product of x1 with x2 hat. And then we have this expression. The only thing, mind you, that is slightly different is in the epipolar constraint. Once we stacked things and rewrote things, this was a vector. Here, A is not a vector, because x2 hat is a matrix. It's a skew-symmetric 3x3 matrix, so x1 Kronecker x2 hat is a 9x3 vector, a 9x3 matrix. And so that 9x3 matrix applied to HS must be 0. So one, and this is interesting because it means that each point pair doesn't provide one constraint, but in principle 3 constraints. In the epipolar constraint, in the general case, we had a single constraint. Here it means this equation is actually 3 equations, because we have 9x3 matrix applied to HS is 0. Yes. 3 equations with 9 variables. It's not good. It means it's not enough to get a unique solution. In addition, there's one issue. There are 3 equations, but unfortunately only 2 independent ones. The reason is that this matrix x2 hat is a skew-symmetric matrix. And that, we remember, is a matrix that has rank 2, not rank 3. And if you do Kronecker products, the rank remains. It doesn't go up. At best, it goes down. So the rank of A is at most 2 as well. So although we have 9 by 3 here, there's only 2 independent columns. And as a consequence, there are only 2 independent equations that each point provides. Only is maybe not the right thing, because it's more than in the general case. So in the planar case, each point pair, each 3D point with its 2 correspondences provides 2 independent equations. And this is why we don't need 8 points as in the 8-point algorithm, but only 4 points. Because each point that we observe provides 2 independent equations. And so with 4 points, we get 8 independent equations in the general case. And this is why the algorithm that comes up now is called the 4-point algorithm. Yes?
4 points with 8 equations and still have 9 variables.
Yes, and so it's exactly like in the 8-point. It means that the null space is then one-dimensional. Because here as well we have the scale freedom. So we don't want the single unique solution, that would be HS equals 0, but we want a one-dimensional null space. And much like in the 8-point algorithm, 8 points are enough to make sure, if they are in a general configuration, to make sure that the null space has only one dimension. Here, in principle, the null space can have up to 9 dimensions, and if we impose 8 constraints in this way, then we can assure that the null space is one-dimensional. And so this is how it works. You take a set of points, typically at least 4 points, and in general 4 points are sufficient. You stack them again in these are 9 by 3 matrices, or 3 by 9 with a transpose. And then if you concatenate them, you get a matrix that is 3n by 9. So each point contributes 3 here, but in terms of rank, it contributes only 2. So the total rank is at most 2n. Meaning here 8. If I take 4 points, I would have a rank of 8. And then I want to solve this equation system. And so this says that the homography matrix stacked as a column, 9-dimensional column vector, is in the null space of this matrix chi. And then I can do singular value decompositions. And so the 4-point algorithm is quite an analogy to the 8-point algorithm, but for that constrained case of planes. And it amounts to computing for the point pairs the matrix chi. Then you compute a singular value decomposition, and then you have to extract from the matrix H that you get as the vector associated with the smallest singular value of chi. You have to extract rotation, translation, and the plane parameters. And this, unfortunately, is a little bit difficult. It's not trivial to get these parameters out. So you saw already the whole derivation of the 4-point algorithm is almost identically copy-pasted from the 8-point. Under this additional constraint of the points living on a plane, then I see that I only need 4 points to get a reconstruction that is unique up to scaling. And so instead of the essential matrix, we estimate the homography matrix H to derive rotation and translation. And then the homography matrix can be composed. I'm not going to go into detail, but there are ways to compose it into rotation, this plane normal, and T over D. So we cannot estimate the translation in general, but only in units of that length D here. So this is the scale ambiguity that is always there, of course, that we don't know how far things are apart. But up to that scale ambiguity that emerges as estimation of T over D here, you know, we can do reconstructions very nicely, and so the 4-point algorithm is actually a very useful tool to do camera structure and motion estimation under the planar assumption. And then the 3D structure estimation is done the same way as we discussed today. You set up a linear equation system in these depth parameters, and then you get the solution. And so that strong constraint that the points we observe live on a 3D plane is very useful because it allows us to reduce the number of required point pairs from 8-point pairs to 4-point pairs. And it's not only that the whole 4-point algorithm is derived in analogy to the 8-point algorithm, but you can then actually go ahead and show relations between the different quantities. You can show, for example, that the essential matrix can be written as T hat times the homography matrix. Or you can show that homography transpose times essential plus essential transpose times homography is 0. These kinds of things, I'm not going to show them, but so there exists a number of relations between the essential matrix and the homography matrix. Okay, I think we'll stop here and continue next time, tomorrow. Thank you.